Beer-Lambert law. So it states that the absorbance of the solution is directly proportional to the concentration of the absorbing species in the solution and the path length. So thus, for a fixed path length, UV-based spectroscopy can be used to determine the concentration of the absorber in a solution. So Beer's law is defined in this equation. So A, K stands for the absorbance is equal to, this symbol is called molar absorptivity, and then B stands for the path length, and C is for concentration. So we have this one. Okay. So this molar absorptivity is constant. And then we have here showing the cuvette, okay, showing the light in. So as you see, this is red, and then after it passes through the sample, um, the lights turn to light, okay, light color red. Okay, and then Beer's law, okay, so in this picture, okay, it shows this red color is called the intensity, okay, intensity before, okay, intensity before. Then after it passes through the sample, we have now I, okay, I is the intensity after, okay, picture showing the reactants and products, okay. So reactants is defined in A is equal to molar absorptivity times path length times concentration, and products is defined in this absorbance is equal to log close and open parenthesis I sub O over I. So we have this, okay. If we want to determine the intensity after, or let's say the intensity before, okay, we can simply, okay, we can simply um, combine the equation, okay, we have like this one, and then we end up in this equation, okay. So I after is equal to I sub O, E to the power of negative molar absorptivity times path length times C. Have example. So we have here, okay, a sample, and then this sample, okay, we have given values. We have molar absorptivity is equal to 0.35 inverse centimeter times inverse molar. Our path length is equal to 2 centimeter, and then our intensity after is equal to 0.1 I sub O. So we want to determine our concentration of this sample. Now, as you see, we don't have the value of absorbance. So using this equation, A is equal to log close and open parenthesis I sub O over I. Okay, and then plugging the given values. Okay, we have this A is equal to log close and open parenthesis 1 over 0.12. So we have our absorbance is equal to 0.9208. So equating this equation to this one, so we have C is equal to A over molar absorptivity times path length. So plugging the given values, we have this one, and then our C or our concentration is equal to 1.3 molar. Okay, so we have this answer. So the Beer-Lambert law is useful for characterizing many compounds but does not hold as a universal relationship for the concentration and absorption of all substances. Because like for example, second order polynomials relationship between absorption and concentration is sometimes encountered for very large complex molecules such as organic dyes. Okay? For data analysis, the graph of absorbance versus the concentration can indicate how sensitive the system is when building a calibration curve. If the slope is steeper, the sensitivity is higher. When the linear least squares regression equation is used, the slope from the line of best fit indicates sensitivity. Sensitivity is the ability to differentiate between the small differences in the sample concentration. So in this picture, okay, so as you see, all molecules absorb and emit lights differently. It depends on the types of covalent bonds available in molecules. If the reactants and products interact with light different at and there is a color change as the reaction occurs, we can monitor the process using spectrophotometer. Based on the picture, we're able to gather data in a form of absorption spectrum. The data show, okay, how much light through a band of frequencies is able to pass through a sample to reach the detector. Thus, peaks that we see show that not all this one, okay, this one, these peaks, okay, show that not all lights of that wavelength reach the detector. It means that it is absorbed by the sample. Continuously doing this process over the duration, okay, like this one, of chemical reaction, we can gather information how rapidly the absorbance changes and how the concentration of the particular substance changing over time. Okay, so we have here the setup or the picture of how we able to get or how we able to get a result. So we have the light source. Okay, so the to differentiate peaks in a spectrum, the bandwidth and the slit width need to be adjusted. So this exit slit, okay, this one can be adjusted. Okay, you can move this one to choose what color you like to strike this sample and or pass through. The instrument ability to separate light into defined wavelength region is known as the spectral resolution. However, since less light will pass through narrow slit, okay, in here, the spectrum tends to spread out. So like this one, okay, so when the light source strike the prism, okay, this prism create, okay, a rainbow colors. Okay. And so wider slit and bandwidth increase the light throughout and therefore the signal produce poor peaks resolution. Now, our goal is to find the balance between the required resolution and the desired signal of light from the sample as the bandwidth increase. So in here, as the bandwidth increase, the peaks collapse. So like what happens sa blue color, okay, it collapses. And as the bandwidth increases, the peaks hold up. Okay, so we have this example. Let's have factors that determine the amount of absorbance. So we have cell path length. So the more resolution light has to travel through, the more light will be absorbed. So the more the path length is um, longer, so the more light will be absorbed by the sample. And then in terms of concentration, the more concentrated the solution is, the more light will be absorbed by the analyte particles. So the more darker the sample or the solution, okay, the more or the less light will pass through, okay, or less light will be detected by the detector. So like this one. So in this example, our cell path length is equal to 2.0 centimeter. Now, as you see, in this part, we have multiple particles. But as it passed through this sample, only few, okay, able to transfer in this area. So again, as you see, in this part, we have multiple particles. And then as the cell path length increased to 3 centimeter, um, less particles able to pass in this area. And as the cell path length equal to 5 centimeter, okay, as you see, the more less particles able to reach in this area. For reliability and best practice, okay, UV-vis spectroscopy experiment and reading should be repeated. So as what we always do in the laboratory, so we conduct or we do several trials or experiment, okay, like 1, 2, 3 trials to get the average result, okay, to have a good, or let's say to have a good um, analysis, okay, analysis. When repeating the examination of the sample in general, a minimum of 3 replicate trials is common, but many more replicates are required in certain fields of work. So the more trials, more accurate, and then more good result will be able to get or analyze. So, and reproducible results are essential to ensure precise, high quality measurements. Standard deviation, relative standard deviation, or the coefficient variation help to determine how precise the system and measurement are, or how precise the result, okay, we able to measure. So a low division or variation indicates a higher level of precision and reliability. So strengths and limitation of UV-vis spectroscopy. Um, no single technique is perfect, and UV-vis spectroscopy is no exemption. The techniques does, however, have a few main strengths listed below that makes it popular. So the same with other instrument, okay, UV-vis spectroscopy, okay, it also has flaws. So it could be the sample is not that, the result is not that good enough, okay, due to other factors, okay. So we have that. So UV-vis spectroscopy is not that um, that perfect instrument. Okay, so the techniques is non-destructive, allowing the sample to be reused or produced to further processing or analysis. So if we are not satisfied with our results, so we can use or reuse again the sample to have another trial. Okay, Measurement can be made quickly, allowing easy integration into experimental protocols. Okay. And then instruments are easy to use, requiring little user training prior to use. So, um, like the same with the other instrument, it needs little training, okay, or reading the manual to understand or to understand how the UV-based spectroscopy function, so that to eliminate, okay, to eliminate like errors or damage of the instrument. So data analysis generally requires minimal processing again, meaning little user training is required. So with that, okay, the instrument is generally inexpensive to acquire and operate, making it accessible for many laboratories. What are the applications of UV visible spectroscopy? So one of that is pharmaceutical analysis. So the medicine, or let's say vitamins, mineral food supplement available in our market, or let's say in our pharmacy, okay, before the manufacturer um, release or deliver that one to them, okay, those samples undergone a several trials to determine the absorbance, or let's say um, the concentration of the vitamins, or let's say the um, materials available on that um, product. So we have bacterial culture. So UV spectroscopy is also used to determine or to monitor the bacteria, okay, used by scientists um, in the laboratory, okay, in bacterial culturing. So UV spectroscopy is still used with this kind of um, data analysis, beverage analysis. So, like for example, um, companies selling soft drinks, milk powder, let's say coffee powder, and powder juice. So those types, or let's say um, liquors, okay, they still use UV spectroscopy to measure the absorbance, and then let's say to measure the concentration of the elements they place or they mix with their beverages. Okay, DNA and RNA analysis, quickly verifying the purity and concentration of RNA and DNA is one particularly widespread application. So we have that application to our DNA and RNA analysis. Um, UV visible spectroscopy is widely used in the field of analytical chemistry, especially during the quantitative analysis of a specific analyte. Okay, so we have that one. And then UV spectroscopy can be applied to determine the kinetics of or rate constant of a chemical reaction. The reaction occurring in solution must present colors or brightness shifts from reactants to products in order to use UV spectroscopy for this application. We also have UV spectroscopy is also used in the semiconductor industry to measure the thickness and optical properties of thin film of wafer. Okay, we have that one. So that's all for my report. Okay, so these are my references, okay, of my presentation. So that's all, and thank you so much.